All right, so the first thing we're going to learn today is how to find the derivative of the natural log of x. And I'm hoping that you all are aware that y equals natural log of x is the same as e to the y is equal to x. We can take both sides of this y equals natural log of x and do what's called exponentiating them. So we're going to exponentiate each side, which means we're going to make it a power of e. So e to the y is equal to e to the natural log of x. And we should know that e to the natural log of x is just equal to x. So that tells us that if y equals natural log of x, then e to the y is equal to x. Everybody good with that?
Mm-hmm.
All right, spectacular. So then what we're going to do is we're going to take the derivative with respect to x of each side of this equation. So on the right-hand side, what do you get?
One.
Okay, good. And on the left-hand side, what do we get?
E to the y dy dx.
Right, e to the y dy dx, right? Because the derivative of e to the y with respect to x has to be done implicitly. So it's the derivative of e to the y, which is e to the y, done with respect to y, times the derivative of y with respect to x, dy dx. Everybody good? So we should be able to divide both sides by e to the y to get dy dx equals 1 over e to the y. But there's a small issue with this, and that's that our original function was all in terms of x, but our derivative is now in terms of y. So anytime we have a derivative that's not in the same variable, if there's a way to turn it back into the same variable, we want to do that. So what can I do with 1 over e to the y to turn that back into x's?
Well, you said before that e to the y is equal to x, so you could just substitute it.
Exactly. E to the y is equal to x, so this is 1 over x. So this tells us that the derivative of the natural log of x is equal to 1 over x. Everybody good with that? All right. What if this was not natural log of x? What if this was natural log of a function, like natural log of u? Could I apply the chain rule to it? Should be able to apply the chain rule to it. So the derivative with respect to x of natural log of u should be the same as 1 over u, so 1 over that function, times the derivative of that function. Everybody good with that? And that's just applying the chain rule into this rule we just proved for natural log of x. All right, so let's take the derivative of natural log of 3x squared, or natural log of u. So the derivative should become what?
One over 3x squared times dy dx.
1 over 3x squared times the derivative of this 3x squared, which is 6x, right?
Yes.
Okay, and so then our x's will cancel, our 6 over 3 should cancel out, and give us a final answer of 2 over x. Everybody good with that or no?
That's good.
All right. 1 second. Okay, so we alternatively could have done this by using some log rules first. Could we have turned this into natural log of 3 plus the natural log of x squared? Is that equivalent?
Yes.
Yeah, and then what can we do with the natural log of x squared?
2 times a natural log of x.
Perfect. And then we take the derivative of each of those things which should be natural log of 3's derivative should be what's the derivative of natural log of 3?
1/3?
Okay, no, the derivative of natural log of 3 is not 1/3. What is 3? 3 is a constant, exactly, and natural log of 3 is a constant. So the derivative of this constant is just 0. Everybody good with that? Derivative of a constant is always 0, right? And so then 2 times the natural log of x just becomes 2 times 1/x or 2/x. So hopefully we can see that even if we broke it down with log rules at the beginning, or if we use the chain rule, we should come out to get the same result either way. Good or no? All right, let's do another one. In fact, why don't you guys try and work through that one on your own. Take about a minute and see if you can work through that one on your own. We get an answer here? Should you get 1 over what to start with?
5 times the cosine of 2x.
5 times the cosine of 2x, and then times the derivative of 5 cosine 2x. And what's the derivative of 5 cosine 2x? That's a chain rule problem, right? It should be 5 times the derivative of cosine 2x, which should be negative sine 2x times 2. Everybody good with that?
Yep.
Okay. The 5s will cancel, and we've got negative 2 sine 2x over cosine 2x, which we could simplify to what?
Negative 2 times the tangent of 2x.
Negative 2 tangent 2x. Everybody good with that? Any questions or issues with that?
Why couldn't we take like the 5 out? Because isn't that what we did last time? Like we took, like we divided it out.
If you wanted to, you could have written. You mean at the very beginning?
Yeah.
Sorry, hold on 1 second. I'll answer.
Okay.
Okay, sorry about that. You're talking about right here at the beginning, natural log of 5 cosine 2x, and then we
Yes.
you wanted to make it into something like natural log of 5 plus natural log of cosine 2x.
Mm-hmm.
Yeah, we could do that if you wanted to. And then when we take the derivative of this, the natural log of 5 part goes to 0. and the natural log of cosine 2x part, we'll end up with we'll basically just end up with exactly this, 1 over cosine 2x, and then times the derivative of cosine 2x, which is negative 2 sine 2x.
Okay, thank you.
Yep, does that help? Does that make sense?
Yes.
Perfect. All right. So next thing we're going to do is we're going to see if we can find the derivative of log base a of x, where a is a real number, a whole number greater than 1. So where a is like 2 or 3 or 4 or something like that. Because we know we can't have we don't do a base 1 for logarithms, and we don't do negative bases or base 0 for logarithms. So, are you all familiar with this change of base formula that I've written here? That log base a of x is the same as natural log of x over natural log of a? Is that something you're familiar with or no?
No, but now I am.
Okay. So let me just briefly talk about this. You can convert a logarithm in any base. So if I have log base 2 of 5, you can convert this logarithm to any other base you want. Most calculators don't have a function that evaluates like bases other than natural log or base 10 for logarithms. So if you were asked to evaluate log base 2 of 5, in fact, let's do a different one. We know what log base 2 of 8 is, right? What does log base 2 of 8 equal?
3.
It should be 3, right? Because 2 to the third is equal to 8. Well, your calculator probably can't evaluate that, but if you use the change of base formula, you can turn it into any base you want by we'll start with doing it in natural log, but natural log of the argument, so natural log of the 8, divided by natural log of the original base, natural log of 2. So if you take out your calculator and you evaluate natural log of 8 divided by natural log of 2, you should get 3. You can do this with any base. You can do this with log base 10. If you type log base 10, which is we write it without the base of 10 attached to it normally, of 8 over log base 10 of 2, should still come out to be 3 on your calculator. You do this with any base you want. Log base 7 of 8 divided by log base 7 of 2 is the same as any of these. I'm not going to go through a proof of it, but that's how it works. You can change it to any base you want. And so normally we will use, everybody good with that? Now that I've already erased it all. I can put it back. Everybody good with this or no?
Yes.
Yeah, okay. And so normally when we convert the base on something, for calculus purposes, we're going to convert the base into the natural log base, base e. So log base a, where a is just a number of x, is natural log of x over natural log of a, where natural log of a is a constant, right? Because a is a number, so the natural log of a is just a number. Everybody good with that or no?
We're good.
All right, so let's take the derivative of this. Well, if natural log of a is just a constant, couldn't I rewrite this as 1 over natural log of a constant, times the natural log of x? And if we were to take the derivative of a constant times this function, the derivative should just be that constant times the derivative of that function. And the derivative of that function is 1 over x for the derivative of natural log of x, right? Which gives us 1 over x ln a. Any questions on that? That is our base form for the derivative of log of any base of x for its derivative. So if it was log base 2 of x, the derivative would be 1 over x times the natural log of 2. If it was log base 3 of x, it'd be 1 over x times the natural log of 3. And we should then be able to throw in the chain rule with this also. So if we have log base a of a function, we should get 1 over that function times the natural log of the base times the derivative of the function. So why don't you guys take a second and see if you can find the derivative of log base 3 of x to the 5th. So what do we get here? Y prime should equal 1 over the function times the natural log of the base times the derivative of the function. Is that what you guys all did? Any questions or issues with that? Everybody okay with that?
Yeah, that looks nice.
All right. Let's real quickly, I threw this in here because I want to talk about this because I saw a couple people made a little bit of a mistake with this on the derivatives homework. Remember that the power rule works for any real power of x. We can use logarithms to prove it. I'm not going to prove it. But a lot of people on the homework assignment for something like x to the pi took the derivative of that as pi x to the 2.14. I don't want you to write it like that. I want you to write it as pi x to the pi minus 1. And everybody get it. So don't, if it's an irrational number up there, don't approximate it. Write the actual value, pi minus 1. So what should the derivative of x to the root 2 be?
Root 2 times x to the root 2 minus 1.
Exactly. Everybody good with that? And what about this other one? This one we would have to use the chain rule. It's u to the pi, so that should become pi times u to the pi minus 1 times the derivative of this 3 plus 5 sine x, which is 5 cosine x. Good or no? All right, I'll assume that's a yes. Now let's take a look at this one. Y equals x to the x, and let's see what we can do with that. Any thoughts on dealing with x to the x power? Can I use the power rule? No, we can't use the power rule because the power rule is for x to a number. Right? Can I use the rule of like a to the x? Can't use a to the x because it's not a number to a power. So we've got x to the x. We have a variable to a variable. Any thoughts on how we're going to deal with that?
Maybe use exponent rules to break it down a little.
Meaning what?
Like how you can add exponents by multiplying them together or something?
Ah, okay, I see what you're saying. No, that's not going to work. Let's use the idea of logarithms that we've been working with. So let's take the log, the natural log of both sides of this. And how will that rearrange the right-hand side?
Because now you can treat it like a natural log of u.
Well, we could, right? So this would become natural log of u, but to take the derivative of natural log of u, we have to be able to take the derivative of u. Do you know how to take the derivative of x to the x?
No.
Unfortunately not. So what else can we do that we've done a couple times here with our logarithms if there's something to a power in them?
It's x times natural log of x.
Right, and now this right-hand side is something that we can deal with. True?
Mm-hmm.
Okay, so natural log of y becomes what on the left-hand side?
1 over y dy dx.
Good. And the right-hand side, we'll have to use the product rule. X times the derivative of natural log of x plus natural log of x times 1. Everybody good with that? Does everybody agree with that so far?
Well, you use the power rule for the right side?
Product rule.
Product rule, yeah. Wait,
Yeah.
So wouldn't it be, isn't the derivative of x, isn't it 1? Oh, wait, yeah, never mind.
Yep. All right, and then we got dy dx equals y times 1 plus ln x as our answer. How do we feel about that answer? The answer should be not good because our function originally started as all in terms of x, but we have something with a y in it. So what can we do?
Redefine y.
Redefine our y. Our y is x to the x. So we'll just change it back to x to the x times 1 plus ln x, and there's our derivative. This method, where we take the logarithm of both sides, is called logarithmic differentiation. And so this is a technique that you'll want to get used to. We'll practice it. I'll give you guys an assignment, a short assignment on it sometime next week to practice the logarithmic differentiation specifically. Okay. But let's see if you guys can take care of one like that on your own. So see if you can use that same idea where you take the natural log of both sides to find the derivative of y equals sine x to the x power. So I'll give you about 2 minutes to do that. You guys finished? Did you guys get an answer for this?
Yeah.
So, okay, let's run through it real quick. Natural log y equals, if you take the natural log on the right, we should get x natural log sine x. Did everybody get that after their first couple of steps?
Yes.
Okay, and then the derivative gives us 1 over y dy dx. And then this derivative is x, and then the derivative of natural log of u should be 1 over u times the derivative of u, and then plus 1 times natural log sine x. Everybody good with that? And as we bring the y over to the right side, we can turn that y into a sine x to the x power. And we can simplify that to x cotangent x plus the natural log of sine x. Good or no?
Can you go over the part again where you got x cosine x over sine x?
Sure. So we're taking the derivative of x ln sine x using the product rule. So the first function is x, and the second function is ln sine x. So u times the derivative of v is this part. So u is x, and the derivative of v, the derivative of natural log of sine x, should be 1 over sine x times the derivative of sine x, which is cosine x. Does that make sense?
Yeah, that does. I just missed one part, so that's why I got it wrong. Thank you.
Yeah, no problem. And make sure you apply the chain rule with that. It's natural log of u. Right? All right, let's look at one more of these. Now this one here is one that we could probably do using the quotient rule, yeah? You agree that we could do this using the quotient rule? What do you guys think? Can we do this problem using the quotient rule or no?
Probably.
We should be able to, right? It's a quotient of two functions. What about if I did this to it? Can I still use the quotient rule?
Yes, but it'd be harder.
Yes, but it'd be more difficult, right? We'd have this extra term. We'd have to use the product rule when we find the derivative of the denominator. What about now? Can I still use the quotient rule? How about now?
I believe so. You just have to do a lot of product rules, right?
Yep, there'd just be a lot of product rules, and that'd get to be really messy and really unpleasant, wouldn't it?
Yes.
Yes. All right, so we're going to try to use this logarithmic method, and we're going to use it on a simpler one because there's no reason for us to throw all this extra stuff in there. But we're going to use this idea of logarithmic differentiation to take a bunch of binomials that are being raised to powers and either multiplied or divided by each other to find a derivative an easier way, perhaps. So first, we're going to take the natural log of both sides. Is everybody good with that? Good or no?
Mm-hmm.
Okay, so then we're going to separate this logarithm out as much as we can. How about like this? Everybody agree that we could do that?
Yes.
Okay. And then what can we do with the exponents?
Multiply them up front. Or in front of the natural log.
Exactly. One second here. Okay, sorry about that. So yeah, we're going to pull all of these out in front. Everybody good with that?
Mm-hmm.
Okay, cool. And so now when we take our derivative, the left-hand side should become 1 over y dy dx is equal to, what can we do with 3 ln 5x minus 4? 3 over 5x minus 4, right? Times the derivative of 5x minus 4. So that makes this derivative actually a lot simpler rather than having to use the chain rule within the quotient rule for those other derivatives. Everybody good with those two little derivatives there?
Yeah.
Okay. And so then that will give us dy dx is equal to y times 15 over 5x minus 4 minus 1 over 2x plus 1. And then all we have to do is turn that y back into our original equation. And so our final answer will be 5x minus 4 to the third over root 2x plus 1, and then times what we just had, 15 over 5x minus 4 minus 1 over 2x plus 1. Any questions on that?
Can you review how you went from like 3 times natural log of 5x minus 4 minus 1/2 times the natural log of 2x plus 1 into the next step? Like where 5x minus 4 was now the denominator. How did you get there?
I'm sorry, say that again.
So how did you get from 3 times the natural log of 5x minus 4 to 3 times 5 over 5x minus 4?
Right, so we took the derivative of both sides. So the derivative of 3 times natural log of 5x minus 4, the 3 is a constant. And so it's 3 over u, which is our 5x minus 4, and then times the derivative of 5x minus 4.
Oh, got it. Okay.
Good?
Thank you.
No problem. All right, everybody good with that or no? All right. We're going to start up with something else here in just a second. I got to help my kid with something. He's having real trouble. He's trying to take a test, and he's having trouble with it. So he can't get it to work. So give me like 2 minutes. Read this, and I'll be back in like Okay, I'm sorry about that. You guys all good? Everybody still alive over there?
Mm-hmm.
All right. He's taking his first tests of the year and having some issues with things to work properly. So, joys of 7-year-old schooling. All right, so we're going to talk about derivatives of inverse trig functions now. And so for inverse trig functions, we have to at least have a little bit of knowledge about inverse trig functions. We're all familiar, I hope, with the function y equals sine x, right? Gosh, I hope so, right? Looks like this, yeah?
Mm-hmm.
Okay. And so when we came up with the function that was the inverse sine of it, what we did was we took the domain of the sine function and restricted it to -π/2 to π/2, so that the inverse function would also be a function, right? We know that a function passes the horizontal line test, then that makes it its inverse a function also. And so if we restrict from -π/2 to π/2, we get all of the y values that we get out from sine, but we don't have any overlap on the horizontal line test, and we end up with the inverse function actually being a function. Does that make sense? I hope. So that's what all this stuff up here was saying, that to get the inverse sine function, we just have to restrict the sine function to -π/2 to π/2 and then take the inverse of it. And once we have an inverse sine function, we should know that this relationship is true. That y equals the inverse sine of x is the same as x equals sine y. Right? Because if I have y equals inverse sine of x and I take the sine of both sides, what's the sine of the inverse sine of x? It should just be x, right? So there's no real difference between y equals the inverse sine of x and the sine of y is equal to x. Everybody agree with that?
Yes.
Okay, so what we're going to do then is we're going to, since we don't know the derivative of y equals the inverse sine of x, we're going to convert it into x equals the sine of y, because we do know how to differentiate both of those. And we're going to take the derivative of this equation implicitly. So we're going to take the derivative with respect to x of x and the derivative with respect to x of sine y. And so on the left, the derivative with respect to x of x is just should just be 1, right? And what about the derivative with respect to x of sine of y?
Cosine y dy dx.
Cosine y dy dx. And so what does dy dx equal? Dy dx equals 1 over cosine y. Everybody good with that?
Yeah.
Okay. Now, what's the problem with dy dx equals 1 over cosine y?
It's not in terms of x.
It's not in terms of x, right? We want it to be in terms of x because we started off in terms of x. So we need to figure out a way to turn cosine y into terms of x. Any thoughts on that?
Use a unit circle triangle.
All right, good. So we know that y equals the inverse sine of x. And so if we draw ourselves a right triangle, what's our angle, right? If x equals sine y, our angle is y. And if x is the sine of y, what can I do on this right triangle? What can I label?
Wait, like the triangle?
Yeah, what can I label on the triangle? Can I label an adjacent side, an opposite side, a hypotenuse? If the sine of y is equal to x.
The hypotenuse is 1, so the height of the triangle is sine of y.
Which is
X.
x, right? So everybody agree that if I have x is equal to the sine of y, I should be able to write this triangle out as x is the opposite side and 1 is the hypotenuse.
Yes.
All right, so then what is the cosine? Well, the cosine should be this adjacent side divided by the hypotenuse. How do I figure out the adjacent side?
You just call it cosine y, or would that be weird?
No, we don't want to use cosine y.
It's the square root of 1 minus x squared.
Right, Pythagorean theorem, exactly. So we know that this side, we'll call it, I don't know, we'll call it a. A squared plus x squared should equal 1. And therefore, a should equal the square root of 1 minus x squared. And a is part of cosine y, right? It's cosine y over, or cosine y is a over 1. So this should become 1 over root 1 minus x squared. Everybody good with that or no? Any issues with that? Could we apply the chain rule to that if we wanted to? Yes, we could apply the chain rule to that if we wanted to. And do you think we could find the other 5 inverse trig functions derivatives in a similar way?
Mm-hmm.
Oh yeah, somebody finally answered. Yes, we could. And here are all of them written out using the chain rule. dy dx of inverse sine of u is 1 over root 1 minus u squared times the derivative of u, and so on. So you want to know and memorize all 6 of these derivatives of inverse trig functions. And I'm going to post up a document that has everything that you need to know the derivatives of, all the rules that you need to know. I'll post that up this afternoon. And so you want to make sure you start memorizing those over this weekend because there's quite a few of them. 6 inverse trig ones, natural log of any base, e to the x, a to the x, product, quotient, power, all those things. They're all in there. So all the trig functions. So you want to memorize them. So let's look at some patterns we notice here. First off, what's the only difference between sine and cosine, or inverse sine and inverse cosine's derivatives?
1 is negative.
Yeah, the co-function cosine has a negative derivative. Okay. What about between tangent and cotangent? The only difference is a negative. Right? And what about between the secant and the cosecant? The only difference is a negative. So if you know sine, you know tangent, and you know secant, the co-functions are the same, just with a negative in front of them. So that should be relatively easy to remember. Any issues with that, or everybody okay with that? All right, let's see. I'd like you guys to take 3 or 4 minutes and see if you can find the derivatives of each of these using those rules and applying the chain rule within them. So take maybe 5 minutes should be good. I'll give you guys 5 minutes to try and find those 4 derivatives. You guys all think you can do that?
Mm-hmm.
All right, give it a shot. You got 5 minutes. Ready to go. Couple more minutes, 2 more minutes, and then we're going to talk about these. All right, was that enough time to do those 4 or no?
Yeah.
All right, let's go through those 4 and then we'll be done for the day. So we got the inverse sine of root x. So this is the inverse sine of u, and our derivative of inverse sine is 1 over root 1 minus u squared. And then we need to multiply that by the derivative of u, the derivative of root x, which is 1 over 2 root x. Everybody good with that? So far?
Yeah.
And then the root x squared is just x, so this becomes root 1 minus x. So we've got 1 over 2 root 1 minus x times root x. Is that what you all got for the first one?
Yeah.
Any questions on that or no?
Wait, is it a rule that when you multiply radicals together, you can multiply the stuff in them together under one radical?
Yeah, you could. So if you wanted to make this 1 over 2 root x minus x squared, you could, or x times 1 minus x. That would be fine also. But this answer is also fine. Either way, I'd be fine with either. Good or no? All right, next one. Inverse tangent of x squared. So what's our rule for inverse tangent? It should be 1 over 1 plus that u squared. And we're going to multiply that by the derivative of u, so times 2x. So what do we get? 2x over 1 plus x to the 4th. Good or no?
It's good.
All right, let's take a look at the inverse secant of root, what was it, x, was it x squared minus 1? Oh, yeah, x squared minus 1. All right, so inverse secant of root x squared minus 1. That derivative, we should know now what the derivative of inverse secant is. It should be 1 over the absolute value of u times the square root of u squared minus 1. And then what do we need to multiply that by? By the derivative of root x squared minus 1. And for that one, we should use the chain rule, which should be 1 over 2 root x squared minus 1 times the derivative of x squared minus 1, which is 2x. Everybody good with that?
Uh-huh.
Any questions on that? That's the chain rule within the chain rule on this inverse trig function. So it's a little complicated, but. All right. First thing we can do in simplification here is cancel out these 2's. So all we have in the numerator then is just what, an x? And in the denominator, we have an absolute value of a square root of x squared minus 1. Well, if we square root x squared minus 1, that's always going to be positive or 0. And so the absolute value of it is kind of redundant. It's not needed. So we can make that x squared minus 1 without the absolute value. And then if we square the square root of x squared minus 1, that gives us x squared minus 1, right? And then subtract another 1 from it, gives us a root x squared minus 2 with another root x squared minus 1 here. And we can then get rid of the root x squared minus 1 times the root x squared minus 1 as just x squared minus 1 and root x squared minus 2. Any questions or issues with that? All right, last one we're going to do here. We had, what do we have? We had inverse tangent, I think, of, what was it, sine 2x. So inverse tangent of sine 2x. If we're going to take the derivative of that, the derivative of inverse tangent of u should be 1 over 1 plus sine squared 2x, 1 plus u squared, times the derivative of u. And what's the derivative of sine 2x? That's a chain rule problem. It should be cosine of 2x times the derivative of 2x, giving us our final answer of 2 cosine 2x over 1 plus sine squared 2x. Everybody good with that or no? Any questions on that or anything else we've done today? All right, that then is it for the day.